Okay guys, so as I mentioned today, we're going to be pushing ourselves one last time for our final skill of the unit, which is finding volumes of known cross sections. And in this example, I'm going to show you exactly what that looks like with the lens of squares. So if you read this problem with me, we can talk through this and then get some more support tomorrow. The base of a solid is the region bounded by the graphs of y equals e to the negative x, y equals -1, x equals 0, and x equals 1. All sounds pretty good from there, and then let's keep going. Each cross-section perpendicular to the x-axis is a square with one side in the xy plane. Determine the volume of this solid. Now, I'm going to try to sketch over the image that I captured from my calculator so that we can also see the vertical lines x equals 0 and x equals 1 here. So far on this picture I've got the e to the negative x graph and the line y equals -1, and now I've input those vertical lines. So in the past, I've had you find the area of this region right here, maybe even spin it around some things to find volumes of revolution. But now the setup here is much different, and we're told that each of these cross sections perpendicular to the x-axis is in the shape of a square. So you know my drawing abilities are not good, but I start with a rectangle, so that's old news. But in this example, instead of spinning that rectangle around and forming like cylindrical things, washers, discs, etc., that rectangle, I'm told, is actually the base of a square. So I need you to think three-dimensionally here and try and envision that that rectangular slice that I've captured is actually the base of a square. And you're going to need to look very critically here and creatively, but what I'm trying to capture is that that square is coming out of the screen in 3D, and it's really producing a three-dimensional solid that's got a square coming out of the region. And essentially this idea is going to mean that I'm putting an infinite amount of those squares within that region, like I showed you on our demo today. And the big idea here is that if I can figure out the volume of one square by integrating that, I'll be able to sum up an infinite amount of those squares. So the good news is, according to what you learned from your geometry teacher long ago, the area of a square formula is nothing new. I believe back in the day you learned that, to find the area of a square, I just take one side and square it. So the good news is this is a square, so that formula still applies. The only difference is I've got some depth here because this is three-dimensional, right? And so to find the volume of that square, I'm multiplying by the little depth. We've also talked in the past about the fact that these things get so skinny that that depth starts to approach 0, and we call that dx or dy in our integral expression. We can definitely talk about that more tomorrow if you guys have any questions about that. But this is really like the jackpot right here, a side squared. That's going to be one square that I can visualize right here if you think creatively with me. And to get the infinite amount of squares, I'm going to take that big idea and integrate it. So the big question here is, just like it's always been, how can I represent that side with some mathematical functions, and what are my A and B? Okay, so here's what I'm going to try and walk you through here to make sure we're feeling okay with this. So the bounds, I hope you're recognizing, since I'm working in terms of x, are definitely 0 to 1. At this point, that should be pretty good for you. And now to figure out what the side is. This is the point in the lesson where I would ask all of you, I'd shout out in the room like, what's my mantra? What's the one thing I need you to remember? And you would all shout back at me, oh, Blakely, it's top minus bottom. So in this case, when I come look over here at my square, I'm asking myself, what's on the top, of that rectangle that I used to form it and what is on the bottom. And it's clear to see here the top is e to the negative x, the bottom is negative 1. So here's my integral setup that I could then use to calculate the the volume of this known solid. One thing to mention, there is no pi out front. I do not have a pi because I'm not spinning this thing, so circles are in no way significant to this process. And I'm really just making sure that the foundation of that integral is the geometric formula for the area of a square. Now, in simplified form, that's the integral from 0 to 1, of course, of e to the negative x plus 1 squared. And if this were a non-calculator question, which it definitely is, I cannot compute that calculus problem without simplifying this thing algebraically first. A box. E to the negative x times e to the negative x. I don't know if this is a surprise to you, but that is e to the negative 2x when I sum up those powers. Here I get e to the negative x, here I get e to the negative x, and here I get a 1. So it looks like this guy actually becomes e to the negative 2x plus 2e to the negative x plus 1. And now comes my favorite part, the time to actually do a little bit of calculus. I can find my antiderivatives using old rules from previous units. The antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x, plus the antiderivative of 2e to the negative x is actually negative 2e to the negative x, and the antiderivative of 1 is x. And now I'll run this guy from 0 to 1. And it looks like my final answer is going to take the form of what I am writing up here. Don't assume that this whole second piece goes to 0 because there are some exponentials here. So I would definitely just play it safe and maybe even leave this guy in the yuckiest form possible. And there is the volume of my solid. Really kind of a cool idea. I'm sure you're begging the question and you're going to lose sleep tonight because you can't get it out of your head. But Miss Blakely, is it only going to be squares that we deal with? And absolutely not. We're going to be looking at all kinds of known geometric shapes that are going to be stacked along our graph and forming these solids. So we're going to get comfortable again with squares like what you just saw here, but also rectangles, semicircles, triangles of all kinds, isosceles, equilateral, and a whole bunch of other stuff. So this is a preview, and if you are really dying to know of what another example of this would look like, I would urge you to watch the second video where I'm going to get into an equilateral triangle. Okay, so for now, this is definitely laying the groundwork for what you're going to be working on more of tomorrow. See you then. Thanks.